Okay, last time we finished the section on rational and polynomial inequalities, right? And we finished with kind of an involved problem, and I wanted to add a homework to that that is not in your notes yet. But if I do, I will send it out to you, and I'll give you adequate time to do it. But in any case, this is definitely something you need to be working problems in the book with, right? The problem we did last time what regarded solving, in this case, a rational inequality. Up to this time, we had polynomial inequalities. This time, you have a rational inequality. And a rational inequality is one where you have one divided by another. One polynomial divided by another polynomial. All right. First thing you do is you make the right-hand side equal to 0 and simplify. Is there a question? You make the right-hand side equal to 0 and you simplify. Right? And so in this case, making the right-hand side equal 0 was easy. But you need to set up for your next step. In your next step, you have to identify points at which the numerator or denominator equals 0. That is, points at which it can change signs. Now, you remember last time in this problem, what happened is we lost all of our work at the very, very end. And so, when I went to recover it, the recovery file didn't have the work in it. So what I did is I went back and I got the work from a previous semester. So this may not match exactly the steps we did last time, but we arrive at the same place. Where we needed to arrive in step 1 here, where we needed to arrive was right here. Right? And so if you have a fraction, it can only change signs when the numerator or denominator equals 0. Oh, by the way, I did put the notes online for this, if using this work right here. So you need to find places where the numerator or denominator equals 0. Those are the places that can change sign. It may not change sign at all those places, but it might. Those are the only places that it can. And so here in part 2, you put on your number line points at which it could change signs. That's the points where it equals 0, or the point in which it has a 0 in the denominator. Right? Now, I did mention this last time. I didn't write this, right? That's why I did that semester. But the two places where the denominator equals 0, positive 2 and negative 2, those go on the number line as places that the rational function can change signs. But you put undefined above those. Those 2 points will never be part of a solution set. Why? Because when you plug them in, they give you 0 and a denominator. On the other hand, this positive 1 right here, it can be part of a solution set. It makes the numerator equal 0. So my recommendation is you put on top of each of these points like this what's happening at that point. Now, in the previous problems, it was all equal 0, equal 0, equal 0. This is different for this problem. Of course, you've looked at this since last time, right? You spent time on this since last time, so you're already like, let's get to the next example, right? So here, we are going to plot. We're going to pick 1 point in each interval. We have 3 points, excuse me, that divides the number line into 4 intervals. 1, 2, 3, 4. Inside each of those intervals, our expression cannot change signs. This left-hand side here cannot change signs inside those intervals. So we're going to pick 1 point in each of those intervals. We picked last time -3, 0, 3/2, and 3. Right? Those are actually the points we picked last time. Even though this is from a different semester, it's got the same points. And then you plug those in, like you plug -3 in, for example, up here. And you can do this a little bit in your head if you want. But you have 3 factors. 1 factor in the top, 2 factors in the bottom. If I plug -3 in, I get -3 minus 1 squared. That is a positive number in the top. You see this fraction, little fraction I got formed here? That's a positive number in the top. If I stick -3 in here and subtract 2 from it, that's a negative. If I stick it here and add 2 to it, -3 plus 2 is -1, which is still a negative. So in the bottom, I have a negative times a negative. That's a positive in the bottom, positive in the top. So that ratio is positive. And so in this interval, it is a positive. From -2 to -infinity. You pick a point in each interval. You pick 0, 3/2, 3. We went through it last time. And you determine the sign. You remember? I saw the sign. You got to look for the sign. Determine the sign. Now, in this interval, you plugged in 0. It turns out to be negative. In the next interval, it turns out to be negative. Now, we expected that because why? Here it changed signs from positive to negative. But here it went from negative, still negative. So when it hits this 1 and crosses this 1, it does not change signs. Why? Because that 1 comes from this factor in the numerator, which is to the second power. Each of these points, -2, 1, and 2, come from one of these factors. That 1 comes from a factor to the second power, and our little rule says when it's to an even power, it will not change signs there. It will keep the same sign as it had before. So in this case, the function, the expression on the left is negative. It hits 0 and stays negative afterward. Then when it hits 2, this positive 2 comes from that x minus 2 right there. That is to the first power. Since that is an odd power, it's going to change signs there. And lo and behold, it was negative here. And when we plugged in 3, we got positive. So it switched from negative to positive. My point behind going through all this is to say that you can validate your steps and know that you are correct. You're plugging these in, and that corresponds, whether it changed signs or not at those points, corresponds to what we expect when we look at these factors, the multiplicities of those factors. These two, at the 2's, plus and minus 2, they're to the first power. It's going to change signs at that point. If it were to the 13th power there, it would change signs at that point. All right? Then for our answer, we're just interested in where the inequality is satisfied. The inequality is this right here. Where is that satisfied? Where up here is it less than 0, and where is it equal to 0? And you see that it's less than 0 in this section, and it's equal to 0 at that point in the middle. So from -2 to 2, not inclusively, from -2 to 2 is our solution set. And that should properly have parentheses around it. Okay? All right? And then on the number line, you can shade that in. Don't confuse. This is a solution set down here. Up here on the number line is the graph of the solution set. That's the graph of the solution set. Any questions on that? You can do one of those. Now, I didn't put a homework in. I need to. I don't know why there's not homework there. But I'm going to tell you a little secret. This is the only chapter. This is the only chapter where I must have bumped my head real hard one semester, and I put some review problems at the end. So these you should save for before the test. Now remember this slide. This is slide number 53. But if you go to the end, right here, that is the little test review. Then over here, you do this. Right here, I'm starting on what is for me slide 61. I have some review problems for this chapter. This is not a contract. I'm not saying if it's not part of one of these 5 or 6 problems that it won't be on the test. I'm not saying that. If we went over it in class, if it's in examples in the book, if it's in the homework, that's what's eligible for the exam. And I outline those things right here. All right, but to help people out, to help you know whether you're prepared for a test, do these problems. Now here, you got a polynomial function that you're going to factor. We haven't done that yet. We're getting to that right now, today. Graphing that, we spent an entire week doing that. And in most times in college algebra, half the class leaves that blank. Don't do that. Let me help you learn those things. But you won't learn them without graphite to paper. That will be on the test at least once or twice. All right? This right here we did. See here. Here are some of the solutions. Okay? There's 4. I think there's 5 down here. Oh, yeah, here we go. This is a sweetheart. This is the one I was looking for. So we don't have a homework, right? But you got this guy down here. This is one of those problems. That's part of the review problems that you can do if you want, right? This is a sweetheart. This one takes a little bit of algebra, right? And then you have the solutions to those. Not the solutions. You have this. These are not solutions. These are actually just answers. Answers. Okay. And then here's the solution set to that problem, right? All right. So let's go back up to slide 53. All of that was a review from last time. I hope that helps. It does not replace you working problems at home between any 2 class periods. If you don't do that, you won't succeed. Now we're going to get back. If you look, I think it's slide 22 in your packet. It's a time I said we had a polynomial function, and I said there's a factored form of the polynomial function under it, and I put magic there. And I told you to put star at the top of that slide. I think that's slide 22. It's something around there. We're getting back now to how to do that. So this is where the book I said is out of order. We did sections 3.1, 3.2, which had to do with polynomial functions. 3.3, 3.4 were rational functions. Not really doesn't follow real well from polynomial functions. It's a little bit related. 3.5 was the rational polynomial inequalities. That's what we just got done with. So this is 3.6. We're getting back to how do you factor and how do you solve polynomial functions. So getting back to just a reminder, a polynomial function has this form right here, right? And this is a theorem. This is a theorem. It's called the rational zeros theorem, and I'm going to use RZT as a abbreviation because we're going to use this all the time. And if you don't use this, I don't know how you're going to solve one of these. All right, so it's the first step in factoring a higher order polynomial is the rational zeros theorem. You got to know it. We're going to be doing some examples here. This says, now, oh, by the way, when we first read through this, nobody understands it. So we're going to read through this and you're going to go, huh? Well, put it this way, you might get it. You might be smarter than me, you might get it. But if you're like, huh? Just hang in there for a second. We're going to do some examples, and I hope that will clear it up. We're going to be employing the rational zeros theorem everywhere. Now, before we get started, I want to emphasize what's the purpose of the rational zeros theorem? Why do you do this? It's this red box over here on the side. It produces a list of possible rational roots. It produces a list of possible rational roots. Okay? So now we're trying to find the factorization of a polynomial function. It's going to have factors. Where those factors equal 0, those are called roots. You remember the most important slide of the chapter? Every factor corresponds to a root, corresponds to a x-intercept. So here, if you have this polynomial function, take note of the first and the last coefficient. The leading coefficient and the last coefficient. This says that all rational roots, just rational roots, I'll get to that in a minute, of that polynomial function, all rational roots are going to have the form p divided by q, where p is a factor of the constant term and q is a factor of the leading coefficient. So you're going to have p over q, p over q. Sometimes the bottom will be 1. So you're going to have like 3 over 1, which is just 3, right? So this is going to produce a list of possible rational. What are rational? What does rational mean? It means fractions. And we're going to consider whole numbers fractions. Because 5 is 5 divided by 1. So we're going to call that a fraction. It's a rational number. So this theorem produces possible rational roots of our polynomial function. A couple of caveats, and we're going to apply this here in a minute. Some notes. The rational zero theorem only finds rational roots. It does not find complex roots or irrational roots. So it will not, if the square root of 3 is a root, it won't find it. The square root of 3 is not rational. It will, if 1 plus 2i is a root, and it could be, this won't find it because 1 plus 2i is complex. So it only finds candidates for some of the roots. Right? The second thing is the possible roots found with rational zero theorem must be checked. They're not, just because the rational zeros theorem turns it up as a root doesn't mean it's going to work. What the rational zero theorem produces are candidates. Call these candidates. Right? And so what we're going to do is we're going to primary the candidates, just like in the election, right? You had all these wannabes for president. They have these debates and people vote. And they go out and do their stump speeches. And so you test the candidates and you pick and you find which ones work, right? Let's do one. Apply the rational zeros theorem to. Now, what is this supposed to produce? A list of possible rational roots. A list of possible rational roots. So, let's take note of a few things. This is A3. That's the leading coefficient right there. This is A0. That's the constant term. And if you look at the rational zeros theorem, we're going to need that. We're going to need all of the factors of the constant term and all of the factors of the leading coefficient. So all possible rational roots, I'm going to write way more than you need to write. All possible rational roots of f of x have the form p divided by q. What is p? Back here. P is a factor of the constant term. So where p is going to be a factor of the constant term, which is 6, divided by, that's right there, divided by factor of the leading coefficient, which is 3. And that's that one right there. Now you ask yourself, let's do the bottom first. What are factors of 3? What integers divide 3 evenly? Well, 3 is prime. So a prime number is only divisible by 1 in itself. So you're going to put down here 3 and 1. However, we're going to have to count the negatives too. Because if 3 divides 3, well, negative 3 also divides 3. So here, very important, we put plus or minus 3, plus or minus 1. Those are the factors of 3. Now, the reason I started at the bottom is that 3 is simple to factor. What are the factors of 6? What numbers divide 6 evenly? Well, you're going to have 6, 3, 2, 1, plus and minus all of them. Now, we're not doing good math here. Or, in other words, we don't write fractions like this. This is symbolic, so to speak, right? We have all, just imagine all the factors of 6 on the top, all the factors of 3 on the bottom. Now, how many factors can I make? Excuse me. How many possible roots can I make out of these? I could put 6 over 1, 6 over 3. I could put 3 over 3, 3 over 1, 2 over 3, 2 over 1, 1 over 3. 1. There's a bunch of them. There's a bunch of them. So what are the factors here? 6 plus or minus 6 divided by plus or minus 1. So I'm going to write this out one time. Plus or minus 6 divided by plus or minus 1. Plus or minus 6 divided by plus or minus 3. Plus or minus 3 divided by plus or minus 1. I'm putting everything over everything. Plus or minus 3 divided by plus or minus 1. Plus or minus 3 divided by plus or minus 3. Plus or minus 2 divided by plus or minus 1. Plus or minus 2 divided by plus or minus 3. I'll slow up for a second so those who want to can catch up. I only got a little more to go, but some of these you're going to see are duplicates. You're going to see some of these are duplicates. I'm going to have here plus or minus 1 divided by plus or minus 1. And then plus or minus 1 divided by plus or minus 3. Everything over everything. Question. We have to simplify that. What do those simplify to? Well, I start off my list. I have plus or minus 6 divided by plus or minus 1 is going to be plus or minus 6. Does everyone see where that comes from? Plus or minus 6 divided by plus or minus 1, that's just plus or minus 6. Similarly, plus or minus 6 divided by plus or minus 3, 6 divided by 3 is 2. That's going to be plus or minus 2. Plus or minus 3 divided by plus or minus 1 is plus or minus 3. We're simplifying. Plus or minus 3 divided by plus or minus 3 is plus or minus 1. Now watch what happens next. The next one is plus or minus 2 divided by plus or minus 1 Plus or minus 2 divided by plus or minus 1 is plus or minus 2. But I already have that in my list. So if it's on the list, you don't put it on again. So that one's already on the list. Plus or minus 2 divided by plus or minus 3. That's not on the list. That's plus or minus 2/3. Plus or minus 1 divided by plus or minus 1. That's plus or minus 1. It's already on the list. And lastly, I have plus or minus 1 divided by plus or minus 3. That's plus or minus 1/3. So this is the result of my applying the rational zeros theorem. The rational zeros theorem produces a list of possible rational roots to this polynomial function. Right? Are all these roots going to work? No. No. Will any of those roots work? Maybe. You can produce a big list like this and have none of them work. So somebody might say, well, Mr. Miller, if none of them work, what good is doing this? Well, you don't know that none of them work until you try them. Now, at most, this is a theorem that's coming up. Since this is a polynomial function of degree 3, it will have at most 3 roots. Now, in fact, it will have 3 roots if you count multiplicities. Right? So if I have x minus 1 squared, that's going to count as 2 roots. Right? So this is what you sought to produce when you applied the rational zeros theorem. This is a list of possible rational roots. List of possible rational roots. Any questions on? We're going to be doing this again and again and again. We're going to be doing this several times. Okay, it's time to do some magic. We might even get through this today. I don't know. I don't know. Can't tell you. All right. You remember slide 22? We had this very polynomial. So I'm going to go back. I think it's slide 22. So I'm going to say C. I think it's that. I'll check it later. If it's not, I'll change it. Okay. We had this very polynomial function, and then I had a factorization below it. I had this factored into factors to different powers. And the exercise on slide 22 was to graph it. And see, this is the disadvantage of the book being out of order, because this was 2 weeks ago now. Right? And so even those who studied it are a little bit going, huh? And then you got some people who haven't looked at it since then, and you're in trouble. I suggest you remedy that. All right? Now, we're going to factor it in these following steps. But first, let me tell you about, are you ready? The secret 0th step. Secret 0th step. What is the 0th step? It's what you do before you do the first step. It's something to check for. And if it works, it's going to save you some time. And we like saving time, right? Because we're lazy bottom dwellers, right? You're going to look for all of the coefficients having a common factor. Are all the coefficients divisible by 3? Evenly. Well, in this case, they're all divisible by 2. If it is, factor off the largest common factor, right? Right? So this equals, I'm going to factor a 2 off. Off of all of those coefficients. What's that going to leave me? It's going to leave me x to the 6th plus 3x to the 5th. Oh, look, there's no x to the 4th here. Keep that in mind. Keep that in mind. No x to the 4th. Minus 6x cubed minus 3x squared plus 3x plus 2. Now, how does that help us? Well, convince yourself that our original function can never be 0 unless this thing in the parentheses is 0. Right? So whenever this thing in parentheses is 0, this top thing will be 0. Because this is just 2 times something that's 0. So here's what we're going to do. We're going to factor this instead. And we're going to carry the 2. Carry this through the problem. I'm going to show you how to do that, okay? That may not make sense now. I'm going to show you how to do that. I'm not worried. Don't be worried if you don't understand that. But we are going to work on factoring this. Now, we're going to apply the RZT to this. Not to the original one, but to that. Because if I can find out where that equals 0, then my original one will equal 0. And factoring that 2 off is going to save me some steps. So, rational zero theorem says all possible rational roots are going to be P divided by Q is going to be factor of the constant term, which is 2, divided by factor of the leading coefficient, which is 1. What are the factors of 2? Plus or minus 2, plus or minus 1. Those are the factors of 2. What are factors of 1? Plus or minus 1. Now put everything over everything. Plus or minus 2 divided by plus or minus 1 is plus or minus 2. Plus or minus 1 divided by plus or minus 1 is plus or minus 1. And that's it. A lot shorter list here than the last example, right? A lot shorter list. Now, let me just show you something. Well, first of all, are there any questions how we got this plus or minus 2 plus or minus 1? You took the factors of the constant term, plus or minus 2 plus or minus 1, divided by the factors of 1, which is plus or minus 1. Right? Let's suppose you didn't do the secret first step. Let's suppose you didn't do the secret first step. And you're working with this original problem. What would this look like? Well, instead of being the constant term being 2, don't write this on your paper, because I'm going to erase it. Instead of the constant term being 2, in the original problem, it was a 4. Instead of the leading coefficient being a 1, the original problem, it was a 2. And so in the bottom, you're going to have plus or minus 2, plus or minus 1. In the top, you're going to have plus or minus 4, plus or minus 2, plus or minus 1. That gives you more possibilities. You'd have the same ones we have, and then you're going to have plus or minus 4 over 1. You'd have plus or minus 4 onto this list. And you'd have plus or minus 1 over 2. Plus or minus 1. So we wound up with 4 possibilities, 4 candidates. If you didn't do the secret first step, you would have wound up with 8. So you'd have more candidates to check. What's the punchline? Do the secret first step if it applies, if you can remember. It'll save you work. All right? So we're going to start checking possible roots using synthetic division. Now, right here, we're going to, these are our candidates. All right. So these are our candidates right here. We're going to start checking them using synthetic division. Synthetic division is something you should have had at some point in your life, but most people forget it. Okay? So we're going to learn by doing it. We're going to be doing it a bunch of times. We're going to be doing it a bunch of times. Right? Here's a little slide on synthetic division on how to do it. It's in the book as well. Right? I got this off of, I don't know, some meme from somewhere. All right? Now watch. Here's what we do. We pick a root. You pick a candidate to try. Plus or minus 2 or plus or minus 1. Take your pick. Yeah, let's do 2. I'm picking that out of thin air. Okay? So you draw yourself a little design like this, and you put your candidate here. 2. 2 is from this list. All right. Now you take your coefficients of your original function. Oh, you know what? This is the function we're trying to factor. So this is important, actually. We decided that that was the same as this. We're going to factor this, right? So we had a 2 up there. And we're working on factoring this inside, this right here. Question, what are the coefficients? The coefficients are 1, x to the 6th, 3, x to the 5th. Remember I said there's no x to the 4th? You're going to have to put in 0 x to the 4th. There's no x to the 4th here. So put in a 0 for x to the 4th. You've got to do that or you'll get the wrong answer. Trust me, I've made all the mistakes. Okay. Minus 6x cubed minus 3x squared plus 3x and 2. That's a big, long list, right? So you put the coefficients like that. Now here's what we do. Synthetic division works like this. You bring down the first number. That's a 1. 2 times 1 is 2. Then you add. 3 plus 2, 5. 2 times 5 is 10. You add. 0 plus 10 is 10. 2 times 10 is 20. This is not looking good. Minus 6 plus 20 is 14. 2 times 14 is 28. Add 28 plus minus 3 is 25. 2 times 25 is 50. Oh, look what we got. Guess what happened? It crashed. We might have lost all that work, but I took a picture of it, so maybe, okay, let's see. This is what happened yesterday I did in class. Okay, we actually, here. Here, we're going to do that. Copy. Paste. All right. We got lucky. We saved some work. All right. So what were we doing? 2 times 25 is 50. 50 plus 3 is 53. 2 times 53 is 106. 106 plus 2 is 108. I'm going to put that in red. What you're looking for, that red number, is the remainder of your division. It's a division process. That red number is the remainder. You're looking for that being 0. So this does not equal 0. What does that mean? That means x equal 2 is not a root. X equal 2 is not a root. What does that mean? That means you can throw it out for the rest of the time. As far as this problem is concerned, forget x equals 2 as a root. Okay? You throw it away. Now what do? We try a different one. Right? We write the same numbers again. 1, 3, 0, minus 6, minus 3, 3, 2. We're going to try a different root, or different candidate. How about minus 2? Right? By the way, if 2 would have worked, if 2 would have gave us a 0, we could try 2 again. But once 1 doesn't work, you don't try it anymore. Let's do the same thing again. Bring down the 1, 1. Minus 2 times 1, minus 2. Add. 3 minus 2 is 1. Minus 2 times 1, minus 2. Add. Minus 2. Minus 2 times minus 2 is a positive 4. Add. Minus 6 plus 4, minus 2. Minus 2 times minus 2 is a positive 4. Add 1. You see how these numbers are staying more tame? You see how these numbers here got bigger and bigger and kind of went out of control? There's a better chance for this one to work. There's a better chance for this one to work. We don't know yet. Minus 2 times 1 is minus 2. Add 3 minus 2, 1. Minus 2 times 1 is minus 2. Add, and you get a big fat Greek 0. Remember I told you were looking for a 0 there. That's the remainder. What does this mean? Now we're going to go back to the most important slide of the chapter. I forget which one that is, but it's one with like a heart on it or something, right? Most important slide of the chapter. If -2, this means -2 is a root. So here, let's go over here and start writing stuff. Means x equal -2 is a root of our function, of that, well, forget, of what we're trying to factor. What does that mean? Anything that's a root, x minus that is a factor. So x minus -2, which equals x plus 2, is a factor. Now here's the disadvantage of having like 2 or 3 weeks in the middle there where we weren't doing, like a couple of weeks. We were doing this like 2 weeks ago. If that's a factor, this is a key step here. This is a place where people mess up. We only got 3 minutes left. Hang in there with me. This means f of x, instead of equaling what it originally equaled, this now equals, you remember the 2? The 2 that we're carrying along the whole problem? Keep that 2 there. We're going to put x plus 2 as a factor. And it's going to be, you can factor off x plus 2 from this blue thing. And according to that slide, those equivalent conditions, that's going to be times another polynomial of 1 less degree. Now, our polynomial here is a degree 6, right? So inside those parentheses go a polynomial of degree 5. So it's going to be something x to the 5th, something x to the 4th, something x to the 3rd, something x to the 2, something x to the 1, and a constant. We don't know what the coefficients are. Where do we get the coefficients? These are the coefficients right here. These. These numbers go in front of these powers of x. The first one's a 1. The next one, plus 1. Next one, minus 2. The next one, minus 2. The next one, plus 1. The next one, plus 1. Okay? So we found a root. When you find a root, that simplifies our polynomial function. And so in our next step on Monday, we're now going to factor this. Next, factor this. All right? We'll leave it there. Hey, we got a minute left. You owe me a minute more studying tonight, okay? Have a good weekend. It's going to be beautiful outside. Go out and have some fun. Create some dopamine, endorphins, and serotonin, right? See you, McKenna.
Bye.
Bye. See ya. Have a good weekend. Take care, big guy. Take care, Cleo.